Hello students, today we'll be learning about how to write the electronic configuration of different elements. First of all, what is electronic configuration? The arrangement of electrons in different orbitals is known as electronic configuration. So for writing the electronic configuration, one must know many rules. So what are the rules concerned? That we'll see now. The different rules are Pauli's exclusion principle, Hund's rule of maximum multiplicity, Afba principle, and extra stability of half-filled and fully filled orbitals. We shall see each one in detail. First one, Pauli's exclusion principle. This principle is given by the scientist Wolfgang Pauli in the year 1926. He said that no two electrons in an orbital can have the same set of all the four quantum numbers. To explain the Pauli's exclusion principle, I am taking the example of helium. Now helium will have two electrons. So we shall start writing the configuration here. So helium has two electrons, correct? So these two electrons will be filled in the first shell. First shell n value is 1. So when n value is 1, the probable value for L will be 1 less than that is 0. And it is the M value or the ML value is dependent on L value, and here you find that this is again 0, and MS for the first electron will be always plus half because it will have a clockwise spin. Now come to the second case. What will be the configuration for the second electron, the quantum numbers for the second electron? N value is again first shell, L value is 0, ML is 0, and MS is then negative half. We have learned that for every orbital, the maximum capacity of electrons will be 2. So what does that indicate? Here you find that helium will follow the configuration, and first electron is having a positive spin, so that is shown by a upward arrow, whereas the second electron is having the same quantum numbers for the rest. The last quantum number, that is the spin quantum number, is having negative value. That means it will have a downward arrow. So what does Pauli's exclusion principle state? It states that no two electrons in an orbital can have the same set of all the four quantum numbers. At least one quantum number will be different. Hope it is clear. The second rule that we are considering here is known as Hund's rule of maximum multiplicity. The statement is pairing up of electrons in degenerate orbitals occur only after it is half filled. What do you understand by degenerate orbitals? Degenerate orbitals are those which have equal energy. Now take the case with the first type of degenerate orbital, that is 2p. So 2p, we know that p orbitals are of 3 types. So that means all are having equal energy, and so we draw it together as -1, 0, +1. This denotes py, this is px, and the last one is pz. So this is 2py, 2pz, and 2px. Clear? Now, what does Hund's rule state? The pairing up of orbitals will occur only after it gets half filled. That means the first electron that is entering the orbital will be entering one of the orbitals here. The second electron, instead of entering it here, it will go to the next orbital. Third one again will be filled up in the next orbital, and it becomes half filled. Only after it gets half filled, the next one, that is the fourth electron, will go for pairing up. Fifth one will go to the next one and sixth one will be entering the next. So this is how Hund's rule will work. We shall take the case of 3d orbitals. We have learned that d orbitals are 5 different types. So we have degenerate orbitals here. 3d orbitals, we can represent it by 5 different boxes. 1, 2, 3, 4 and 5. So we have the values -2, -1, 0, +1 and +2. So here you find that the different d orbitals involved are dxy, dyz, then this is dz square, then we have dxz, and finally dx square minus y square. Now how do the filling up occur here? First electron in the d orbital will evidently enter the first box. Then the next electron will enter the next orbital, followed by the third one in the next. Fourth one will enter in the fourth column, that is the fourth orbital. Fifth one will enter in the fifth one, and the sixth one will go for pairing. So then you find that the sixth electron will enter for pairing up in the first orbital. Then it will be followed in this regular manner and then filling up occurs. So this is what is called Hund's rule. Never you find that in the p orbital, d orbital or f orbital, the filling up can happen in this manner. So if it is 2p, the second electron will never end in this manner. So this is totally wrong. Have you understood? The next rule that we have to learn is known as Afba principle. Afba is a German word for building up. So this rule is also known as N plus L rule. So it gives an idea about how the electrons are entering in the different orbitals based on the increasing order of their energies. So to understand the Afba principle, we have a simple rule for that. We just arrange the different orbitals in the different shells in a regular pattern, and the first shell has only one orbital, and that is 1s. So we arrange 1s here. Second shell will have two different orbitals, 2s and 2p. We are arranging it in the same line. Now, third shell will have 3s, 3p, 3d. Fourth one will have 4s, 4p, 4d, 4f. 5s, 5p, 5d and 5f are the different orbitals concerned with n is equal to 5. So how will the filling up occur? So to find out what is the order in which the different orbitals are being filled up, we just have to draw diagonal lines one below the other. So if we have the first filling occurring in 1s, then it comes to 2s. After filling up 2s, it goes directly to 2p, fill up 3s and then go to 3p, fill up 3p, then go to 4s, then 3d, 4p, 5s, then come to 4d, 5p and so on. So if you just arrange the different orbitals up to n is equal to 7, we are able to fill up all the electrons in the different 118 elements. So according to Afba principle, the electrons are entering the different orbitals in the increasing order of their energies. Coming to the last rule, which is known as extra stability of half-filled and fully filled orbitals. In the case of degenerate orbitals, again, when we just check the stability of the different orbitals, we find that half-filled orbitals and completely filled degenerate orbitals are having extra stability due to their exchange energies and the symmetry in the filling up of electrons. So here, if you take the case with 2p, find the 2p orbitals. If it is half filled, it is having an extra stability. Same as the case with 3d. 3d orbitals, we find 1, 2, 3, 4, 5 half filled 3d orbitals as well as fully filled orbitals of that is the degenerate orbitals are having extra stability, and this occurs due to the symmetry in the orbitals and exchange energies that we'll see it in detail in the next video. Thank you.